Okay, thank you guys. Thank you for attending this session, and for those of you that are going to be listening to it to the recording, thank you for attending. I'm going to be talking about AI and specifically use cases, and with the view of how I, as a practitioner, consider the use of AI. And there's a number of different applications. I'll be quite transparent to you guys today that the work that I do in terms of AI, machine learning, all of that is pretty much done, or what I focused my career on is in the consumer behavior part. And I mention that because you'll see where much of the sort of the excitement and and energy has come from AI, which is really outside the area that I've spent most of my life in. But we'll talk more about that later on. So where are we today? Well, today, if you take a look at the three things. I mean, we all know, like, there's lots of technology going on, i.e., lots of advances that we're hearing about in artificial intelligence. I'm inundated with articles and different research work that I see that's going on about trying this type of technique or algorithm versus another. And so we're seeing these advances with technology, and again, the technology, and I'm talking about not just the math but the computers, and the way to process data has allowed us to really take advantage and leverage all of this technology. And it's also created automation. We live in a much more high environment that we did certainly when I began my career, and there are risks to that. I give a 2-day seminar on data science, and I discuss some of the pitfalls and pratfalls of automation that we need to think of. But that's we are in that environment where we want to automate as much as we can in order to solve more and more business problems. But we have to kind of step back. We have to kind of step back and say, okay, are we indeed solving the business problems? Because it's easy to rely on automation to to solve all the problems that are out there. And the third area is easy access to more data. And that's what I'm all about. My emphasis has always been on the data. And now we have lots more of it, as we all know, with the big data environment. When I began my career pretty much in the structured data world, rows and columns. Now we have data because of the internet and digital. We have data coming in from semi-structured, unstructured formats. I now teach a course at several schools where we're teaching students how to go out and attack semi-structured and unstructured data. So there's just a lot more data that we have to deal with. Why the popularity of artificial intelligence? Well, really, this is it. It's really the work that was done by Geoffrey Hinton, who's at the U of T, and then also, what's his name? Trying to remember the gentleman's name from the University of Montreal, Joseph Bengio. These two pioneers. And they call them pioneers. We're really Canadian pioneers in the area of AI, but all their work was done in the area of image recognition, which you can see here. I'm not going to get too much into the mechanics, but what it's done. I mean, if I think of the business applications of AI, what it's two clear applications are auto insurance claim processing. So back. And I'm talking about this because I've done a lot of work in the auto insurance area, building models to try and predict how to price a certain policy, and we use claims, a lot of other information to try and help us to predict that. In the past, we had to use a lot of sort of numbers and what historically been done. We could never take advantage of pictures and what that meant in terms of the value to a claim. Now we can. And we can do the same thing not only with auto insurance, with property management. So I also built models to predict the how much a policy should be charged if somebody was trying to get insurance on a property. So how much should we charge that particular customer on their policy for that for that particular property? And again, we looked at historical data, numbers, and all that. But again, we didn't, we did not have the advantage of using images. We now do. And then the last area is, of course, is the identity detection, to be able to detect certain individuals. And then the last bullet point that I've talked about is this GANs, which is this generative adversarial networks, which works by the premise that we can actually start to create false images. And the way it works is that the AI is actually creating two models. It's creating sort of what they call a true model in terms of predicting that image, but there's a second model going on which is actually trying to fool it, which is actually trying to identify or seeing if it can replicate exactly what the first model is doing. And it gets to a point where that first model looks at that second model and says, oh, it's the same image. And you've ultimately ended up creating a false image. But this is the image, or the mathematics behind that are called GANs, or generative adversarial networks. So those are some of the things that are done in images. The other area of application is NLP, where again we see text which is broken down into n-grams. I'm not going to get too much into the mechanics because I'm kind of doing a broad suite of different business applications. But here you're taking a look at text and you're putting it into n-grams and into vectors, which are then put into this kind of a network, or a neural network, whereby these vectors are all being used to predict what that next sentence should be. And there are various techniques. Some of you may be familiar with them, which is LSTM, which is the long short-term memory, which places more heavy weights on the more recent information as opposed to the past. And so again, some of the applications you can read here below are speech recognition, medical diagnoses, review of legal cases and precedents. So again, a lot of this stuff is being used in, I would argue, in a very good way. Certainly, if you talk about medical diagnoses, I don't think the doctor's ever going to be replaced, but this will be more of a facilitator for the doctor. Like, how do I facilitate and increase the level of knowledge that doctor already has, and by helping him simplify, or at least simplify his job, and at least using information better to help him make better decisions. Some of the challenges with AI, and a lot of you may already know this, is explainability. I'm showing you a model I built a long time ago, which is pretty basic. It was a response model, which basically looked at the key variables here within the given model, the impact on response, and then basically its contribution to the overall equation. So when I would present this to senior level people, this is a bank model that I built. If I presented this to senior level bank people, they could pretty quickly understand the key drivers of the model. Neural nets, the jury is still out. Like, we're still not at that point. Now, I'm not saying for images. I know there's heat maps and that which can be used to perhaps highlight facets of the image which are contributing more to the prediction. I believe it's a little harder here with neural nets because you have many layers, as we all know, and so it's not typically as straightforward as other types of models. Having said that, we all know that data science is the discipline behind AI development. I don't think there's any news behind that. We know that the resources and tools are there, and that they're getting better and better. I know that there's all kinds of different modules or routines that I can call up, from the open source area using Python, and that's fine. But the age old time-resistant problem remains. Like, are we really solving the right problem? Which I'm going to spend a little bit more time talking about. So AI is a tool, and that's the way that I look at it. It's a tool and still needs problem solvers. And the technical and mathematical skills are not enough, because you need to understand the output of what AI is delivering and the levers, I would say the levers that you need to pull. But you need a lot more, there's a lot more knowledge that one needs to do, or one needs to have in order to be able to solve the right problem. So is AI going to help to alleviate this gap in problem solving? Yes and no. At its core, the mathematics is very powerful, and if there is a trend, as I've seen, if there is a strong trend in the data, AI is no question is the best mathematical tool to use. If there is indeed a very strong trend in the data, and I use the word if. I hope to show you later on what I mean by that. It's actually the last few slides of this presentation. But you can see here's a simple schematic. Because we have AI, we have a simple one hidden layer network versus more of what I call a deep learning network, where we have multiple hidden layers. And so we have this great power to use mathematics to really deliver high powered solutions. But again, it's, are we using the right solution within the right instance? So, can AI fully address this challenge? Again, there's intense mathematical computation going on. The people using AI need to understand the mechanics behind the math. So again, the concept of the number of nodes, within a given layer, the number of hidden layers, optimization routines. And again, you'll notice I've made a note, there's all kinds of different optimization routines. A lot of them, as I would say, are different flavors of the gradient descent type routine. We have learning rates, dropout rates, training, testing, and validation. So we have all these things that are available to us as users to take advantage of and to play with, to see if we get, to see if we can indeed get better performance. And I'll discuss how I, look at performance at the end of this presentation. And so I like this chart because this chart really depicts the human versus AI. I presented this at another conference, and it went over very well, because I wanted to show the human brain. And this is something I got from, I think, I'm not sure if it was some medical journal or whatever, but this is the human brain. And you can see here, this is looking at what the human can do that AI cannot. And if you take a look at the lower area of the brain, which is like kind of like, sort of the basic, like the higher level thinking is up on the top, is all this sort of brown matter. Down here is the kind of closer to the brainstem, which are the basic functions. You see here that look at these functions at the lower end of the brain. Speech recognition, language processing, and image recognition are all at the lower parts of the brain, not at the higher parts. So I like to look at this because it kind of tells me where AI is versus where the human being is in terms of providing that fuller answer. Not to say that we shouldn't be using this technique because of its power to really plow through data, to plow through large volumes of data. And so the image advantage versus AI is the ability to think laterally and linearly. So, an AI at this stage tends to be more linear. Now, that's not to say it's going to be like that all the time, but right now it is more linear. I think there is some thinking from what I've been reading, or some literature that I've heard of, that I'm sure there's work that's being done to try and make a lot of this work, try and make AI tend to be more lateral. So I wanted to kind of just give you my perspective on AI and on the human being in terms of like what AI is doing in terms of its processing, and in terms of what the human being is doing in terms of their processing when they process information. So I'm going to kind of explore this within the data science process. So if I look at the data science process, we have kind of these 4 stages, which I spend a whole course talking about these 4 stages, and I'm not going to do that today. And I actually wrote a book on these 4 different stages. But what I wanted to talk about is that in these 4 stages, the practitioner is involved in all 4 stages. And AI versus the practitioner certainly emphasize certain steps. And that's what I'm going to talk about, or you're going to see in the next slide. So again, practitioner, human being is involved in all 4 areas. And yeah, the human being will emphasize certain stages, and AI will emphasize certain stages. So if we take a look at that 4-step process, we have the human being. The human being is very good at identifying problems and then actually working the data. As I say, working the data to solve the particular business problem. Where AI comes in, which is down here, is the last 3 stages, which is applying the analytics tools and then implementing or deploying these analytics tools. So this is where AI is emphasized, and this is where the human is emphasized. But keep in mind, the human is also involved here in terms of using the right tools, and also involved here in overseeing. So think of it, if the human being is overseeing the use of these tools, and then its actual deployment. And so the best way to understand AI and its effective application is through case studies. And that's what I'm going to do for the remainder of the presentation. And the common thread in all these case studies is, again, the ability of the data scientist to understand the business problem and to work the data. So this is really what I'm going to be emphasizing, okay, is the business problem and then working the data to use the right solution. And in most cases we adopted a machine learning or AI type model. But users must understand the mechanics behind the math. So case studies that I'm going to look at hopefully help you understand the kind of thinking that's required, and then also some of the ML applications that we used. And the other thing I hope to demonstrate is that each of these cases, I hope that they illustrate the breadth and lateral type thinking that I was just discussing, which is an advantage, a big advantage of the human being versus AI. And so here's case study 1, where I had a travel company and they wanted to improve their level of operations when their customers encountered car problems. So here, that was the problem. So how do we use our skills to do that? Well, what we did is we realized that there was a customer satisfaction survey that they had. And then they also had, excuse me, but they also had a data center that looked at what was going on at the actual scene of the event. So we were able, without getting too much into the mechanics, we needed to basically integrate both these data sets, both the data center and the customer sat survey, so that at the end of the day, we actually built a model. So we built a model to identify the key operational tasks that improved the overall customer service. And so what this did, this basically presented back to the client, is and again, we used to, this was determined from the model. The key drivers was to reduce the time between the call and the arrival of the tow truck. We needed to reduce the number of calls that were transferred to the other agent, And again, the other variable, which was kind of interesting, was that people that lost their car keys were more highly dissatisfied. Don't know why, but that's what the data told us, and that's what the model told us. And so these are the three things that the company could leverage in terms of actions. So what actions can we do to make customers more happy? The next case study was looking at a travel company not able to service its customers during extreme weather. So again, this is again looking at this company to provide roadside assistance to customers that had a car breakdown. And obviously, these customers would have more of a car breakdown during extreme weather than than non-extreme weather. And so they were encountering huge, I would say not huge, but encountering large forecasting issues in terms of like not forecasting the right number of staff to handle all the phone calls. Because if you think about it, if you think about if you're on the if you're driving and you're in the middle of a snowstorm, pretty likely you might encounter some kind of difficulty. You're going to get on your phone and try and call the call center to get help. Well, you're probably not going to be the only one. There's lots of other people. And so we needed a model that could predict this number of staff that should be able to man all these phone calls. And so that's what we did, was to predict the call center volumes for roadside assistance. So if we could predict the call center volumes, we could then achieve better staff resourcing. And so what we did is, in this case, we used weather data. So we were able to get weather data, which is open source. And these are just some of the variables that we looked at. You can read them here. And we developed two models. So we developed a model to predict the extreme weather events. And then we developed another one that, given that there was an extreme weather event, the model to predict call volume. So what was the call volume given that an extreme weather event was likely to occur? So we had these two models in place that we could use to help forecast the number of people at the call center. And so what that translated to was like basically 25 less dropped calls per hour. So it did help them. Could we get better? There was a lot, I'm going to be honest with you, there was a lot of noise in the data. I believe we did make some improvements, but again, there was a lot of noise in the data. And so we did actually get to a point of diminishing marginal returns where the best we could do was 25 less dropped calls per hour. The next thing I want to talk about was mobile data, whereby we were looking at, could we use mobile data to predict the likelihood of somebody coming back again, i.e. of somebody making a return visit. And so again, these were models that we built. Again, just looking at that device. So again, looking, because as you know, with mobile data, maybe some of you don't know, with mobile data, each mobile device has a unique MAC ID. So that obviously, if you lose your phone, you get a new MAC ID. But your MAC ID, think of it as almost like a loyalty card. So your smartphone is almost like a loyalty card. And as you travel with it, based off the GPS of the phone, we can see where you're going and where you're not going. And we can do a lot of location analytics around that phone. And conversely, we can also build models to help predict the likelihood of you going to a certain location and the likelihood of you not going to a certain location. So the challenge, though, was again, I'm just showing you, this is a snapshot of raw data. The point I'm trying to make here is that we had to work with suppliers or partners to really take a lot of this almost packet type data. It's almost like machine type data, to convert it into kind of structured fields. And I'm keeping it very simple, where we had like the event date, we had the MAC ID, we had this is when that location. This is actually another field that looked at how close they were to the device within the store. And so this gave us information. You can see the date. The data information actually gave us information as to when they first came into the store, how long they were in the store, and when they exited. So we could take a look at, information. We could take a look at, time. If I take a look at time variables, the time variables we could create is like, what time of day do they come into the store? So do they come in the morning, evening, or afternoon? What day do they come in? Are they more likely to come in on the weekend, weekday, or season? Do they tend to come into that store more often during the summer or the winter? So we could create all these derived variables, and we could create change variables as well, because we had this data over time. And so we created this target variable of defection, whereby all customers had some activity in the first 3 months, and then defectors were defined as having basically no activity in the 4th month. And so that was kind of the very simple methodology that we used in building the model. And what we did is we ended up building a model. We did some work in terms of looking at customer return. We found out that there was a lot of customers that came once and never came back again to that store. But the model we built, so for existing customers that do repeat, we built this model, which is looking at observed repeat rate. And we have a pretty good model. If you take a look at the curve here, the curve is trying to predict. So on the x-axis, is what we're predicting to come back versus what's observed. So this represents the observed repeat rate, and this on the x-axis is what represents the predicted. And you can see we have a pretty good what I call a Lorenz curve, where we're actually rank ordering quite well in terms of what we're predicting versus what was observed. But once we get down to the bottom to 60% of these visitors, the bottom 40%, we don't seem to be able to get much differentiation, which would suggest the use of more information. And when I say more information outside of just location type behavior. And so using that kind of information, I believe, would help to perhaps maybe increase the slope of this type of curve. The next one I want to look at is another situation where this company was looking at trying to develop effective pricing strategies for its liquor products. And the data challenge was they had very, very limited data. You can see less than 100 records. So you can say, okay, well, what did we do? Well, we kept it very simple. We used basically a multiple regression model to arrive at one option for the math-based approach towards pricing. Obviously, as most of you, maybe many of you know in the audience, the use of an AI model is going to be very, very marginal. We all know that AI works well with large volume of records. I hope to show you that at the end of this presentation. So obviously, small data and looking at what we did using I would call multiple regressions certainly advanced statistics, but certainly not as advanced as AI. But using that kind of technique allowed us to get very, very good results. And the solution we built here, most of you will recognize this is an AUC curve. And again, this is the decile lift chart in terms of being able to predict. And so this is a pretty good model. Again, this is something we'd want to test, but this is a good model when you just take a look at the as I said, the AUC type curve or this decile chart. Next one was a company, again, I'm surfing through these cases to try to illustrate the problem and what we did to solve the problem. In many cases, we used models and AI models to do that, or at least looked at them. Company wants to predict water demand at a point in time. And this is the actual data or the volatility. The problem we had is we couldn't estimate or use a predictive model in any way to predict water demand at a given point in time, because that's what they wanted. They wanted to predict water demand precisely at a given point in time. But we couldn't, given what we were seeing, we really couldn't do that, at least for now. So what we did is try to look at it in a broader way. And so we looked at, rule-based insights. We looked at broad factors that drive water demand. And basically what we came up with were just some simple reports like this that looked at average demand in terms of seasonality. And again, looking at even at a daily level, like time of day. So that kind of told them, it gave them somewhat of a solution, i.e. more business intelligence than predictive, that told them what the average demand would be at certain times of the day. And so these are the case studies that I wanted to talk about, which I think illustrate the notion of problem, using data to solve the problem, and then potentially developing models to help us achieve that given solution. The next thing I want to talk about is work that I did looking at AI models versus traditional machine learning models. So these would be models, when I say traditional machine learning models, these would be models like logistic regression, multiple regression, or shade, any of those kinds of models. And I compared them to AI. And so what I did is my approach was I looked at a variety of different practical examples. I explored, as I said, traditional models versus neural net, deep learning. I looked at a number of different hidden layers and node options to find the neural net, to find the best neural net option. How I'm going to measure success, that's the thing we need to look at, right? If I'm going to compare one versus the other, what's my measure of success? Well, it's going to be lift. And what I mean by lift is the steepness of the Lorenz curve, or how well the model rank orders records versus the model behavior. And I'll show you that in the next couple of slides. So that's how I'm going to measure success. So any kind of improvement, I will see a steeper curve, because that is my report card. If I can get a very, very good model, regardless of whether it's AI or not AI, I want to see that model or that tool deliver better rank ordering, i.e. a better AUC type curve. And I looked at both small data and big data, or big data as much as I could find it. So the exploration, again, these are some of the things I explored. I looked at 1, 2, 3, 5, and 10 hidden layers. I think I actually looked at 20. I looked at a number of different nodes for each hidden layer. I used the gradient descent approach. I looked maximum number of iterations to conversion was 1,000. And the validation approach that I took the development sample and I split it into 60% training, 40% testing, and then I had a third validation sample, which was about the same size as my development sample. So that was the approach. I then went in and I looked at a number of different models that I built over the number of years, and I started applying different different AI algorithms against that. And so what you're going to see here is I'm just showing you one example, because for all the cases that I looked at, I pretty much found the same result. And again, this is looking at pretty much small data, under 300,000 records. And so this is basically what I found. The green line, I believe the green line, there's two lines here. There's a green line and a purple line. The green line and the purple line, I think the green line is the stepwise, and the neural net is the purple line. You can see that down here, this is an acquisition model that I built. And so in the acquisition model, I have deciles down here, which is what I'm predicting. So I am predicting in my top decile, these are going to be my best responders. Or down here, this represents a group of people that are going to be, that I predict to be my worst responders. So deciles is what I predict. The y-axis is what I observe. And so you can see when I look at the two techniques, not getting any, not getting really any difference. It's the same thing. So, and I pretty much found that, and I looked, I think, at 10 to 20 different models. So I then started to look at bigger volumes of records. So I looked at data with over 1 million records. And this is what I found, okay? So I took a look at one model, which is a reactivation model that I built for a not-for-profit. And here I start to see some slight improvement with the, again, the purple line is the neural net. Again, it's only a single layer. And here's the traditional stepwise. So again, I start to see some slight improvement. And this is with reactivation. I then did something with the property insurance model that I built, which is looking at the likelihood of having a claim. So my objective function or target variable was the likelihood of having a claim. And here I had a single hidden layer. So I only had one hidden layer, and I'm comparing it again to my stepwise. And here you can see I'm starting to get improvement. And then when I compare that, when I take that to look at several layers, so this is when I had multiple hidden layers, okay? And I can't remember how many I looked at. It may have been 10 or 20, I'm not sure. But this is where I looked at multiple hidden layers. You can see I get significant improvement in terms of the AI. So what I'm trying to say here is as a data scientist is I like to have the data demonstrate to me, or the results demonstrate to me. And again, I'm looking at this in my own field of consumer behavior. So, you know, I've talked about image recognition and NLP, which are areas that I'm familiar with, and I'm very familiar with the applications that are being used. But it is certainly not an area of business application or how I would use models to improve that. It's not basically where I come from. I come from the world of consumer behavior. I might use elements. So I might use the ability of, I might use the output of a score from a picture as an input variable for a model in claim risk. So I might use the output of one AI model as input into another model. I guess the classic example of that would be using an image, you know, one of these claim, you know, one of these claim event images, and using that as input variables. So so again, you know, why, you may ask, why am I seeing this? Well, number one, when I was thinking about this, number one is I have more data. And we all know that in artificial intelligence, the real oil of AI is lots and lots of data. And this is why AI was never so was always tough for it to be a recognized technique. We could never use large volumes of data. Now we can. And because we can use large volumes of data, there's a lot more opportunity to demonstrate these kinds of things. The second component is the pattern. There needs to be a pattern in the data. And again, this is a property model, which arguably you could say that the pattern is a lot stronger because it may be less, the patterns may be less determined by consumer behavior than by wear and tear. So the patterns are more pronounced with property than they are with, let's say, auto claims. And again, I'm hypothesizing, but you know, this is what I'm just showing you what the data told me, and I'm trying to rationalize why I'm seeing what I'm seeing. People can always dispute me on that, but you know, as I said, this is what I saw when I was looking at the when I was doing my R&D work in this area. And so my conclusions are, I purposely skimmed through these case studies. Why? I wanted to better understand how the solutions need more than just AI to solve a given business problem, and to then define the appropriate solution. At the same time, you know, I hope that our R&D, so the work that I just did, that I just showed you in the last few slides, I hope that demonstrates that AI is not necessarily the panacea. And again, it needs to be measured like other techniques. And again, I know we're getting into a world of automation where maybe you say, why don't we just apply AI? Because we know that in a perfect world, it's going to deliver the best solution. Have to be careful about that. Explainability is always going to be an issue for us as data scientists. And my last point, before I turn it over for questions, if there are any, is the need is not better AI algorithms, but more importantly, practitioners who can effectively apply them. And so this is the real need. And as I said, this is something I've had to learn over the last five to 7 years, is understand more about AI and about the different levers that can be used to develop algorithms. So again, as data scientists, it's always incumbent upon us to be open-minded and to look at all the solutions that are out there. So that's it for me. Hope you enjoyed today's presentation. I'm going to turn it over for questions.